Hello, and welcome to Let's Build on AWS. On this episode, we're helping Richard and Mary build their first IoT app so they can get started creating IoT projects for their food startup. I am Anna, and I am a developer advocate at AWS, and Vinicius Sanger has worked with me on the other modules, so make sure to check them out as well. The previous module, we had an introduction to IoT and connected our ESP32 board to AWS IoT Core, sending and receiving MQTT messages. In this second module, we're going to customize a push button and create an IoT call waiter button. So let's get to it. We'll start this module connecting a push button to the ESP32 board to better understand how they work together. We're going to create code that will detect when the button is pressed and perform an action based on it. After we understand how the push button works, we'll customize it into a call waiter button. Our call waiter button will connect to AWS IoT Core through the MQTT protocol, sending and receiving messages. This is the architecture of what we are going to build, and whenever the button is pressed, we're going to send a message containing the table name, the device name, and the device time. So what about the hardware required for this module? We're building on the previous module, but we're also going to require some additional hardware. We'll keep using the ESP32 board and the micro USB cable to connect it to our computer. We're going to need a breadboard, also known as a protoboard. This is a base for prototyping electronics. We're going to need some jumper wires. These are electrical wires with connector pins on both ends, and they are used to connect components on the breadboard. Finally, we'll use the push button to trigger our call waiter message. The sample code for this module and the other modules as well is available on our GitHub repo and can be accessed with the link or QR code below. Okay, so the first step is to start building our circuit. The first thing we're going to need is the breadboard. The breadboard is a base for prototyping electronics. The pins on the breadboard are connected by metal strips that live inside the breadboard. This is really useful because it doesn't require us to do any soldering, and it allows us to reuse it for different prototypes. The breadboards can vary in size, but they usually look something like this. The breadboard has some distinct areas that are very important that we understand. The first one are the terminal strips. They live in the middle of the breadboard, and they are used to connect electronic components. In this orientation that we have right here, the pins on the terminal strips are connected in columns. The terminal strips are divided by a notch that lives in the middle. The key takeaway here is that the columns above and below the notch are not connected. So the notch splits the terminal strips in half, and only the pins on the same side of the notch are connected. This is actually useful because it allows us to work with more components. The other area of the breadboard is the bus strip. They are used to provide power to the electronic components. In this orientation, the pins on the bus strips are connected as rows. The bus strips are usually labeled with a plus or minus sign or a red and blue strip like we see here. These markings are used just for reference, but the convention is to connect the power supply to the row marked in red and the ground to the row marked in blue. The back of the breadboard is usually closed, but I opened mine up so you could take a look. This is what the metal strips inside the breadboard look like. They are the ones responsible for connecting all the pins. These are the metal strips connecting the pins on the terminal strips and on the bus strips. We just have to keep in mind how breadboards work and how the pins are connected so we can safely use them to build our circuits. Now that we have our breadboard, the next step is to connect our ESP32. On my breadboard, this ends up leaving the GPYO pins on the top of the ESP32 inaccessible. But this is fine for now because I won't be using them on this module. We can overcome this by using female to male jumper wires to avoid having to place the ESP32 directly on top of the breadboard. This would enable us to use all the pins on the ESP32, and Vinicius is going to show you how to do that on the next module. Okay, so the first thing we usually do here is connect the power from the ESP32 to the red bus strip on the breadboard. We're also going to connect the ground pin on the ESP32 to the blue bus strip on the breadboard. From here, we can use the bus strip to connect both power and ground to the other components that will be used. With our ESP32 connected, it's now time to connect the push button. We're going to connect pin number 23 on the ESP32, this one right here, to the push button. We're almost done with our circuit, but first let's talk about how the push button works. Here's our push button connected to the ESP32. The pins on one side of the push button are always connected. For instance, pins number 1 here, and pins number 2. But when the push button is not pressed, the pins on this side are disconnected from the pins on this side. They do connect when we press the push button and this switch closes, then we have the connection from pins number 2 to number 1. So right now, our push button is connected to pin 23 on the ESP32. And we want to be able to send it a low voltage to pin 23 whenever we press the button. One way to do this is by connecting the other side of the push button to the ground pin on the ESP32. So let's do that. We're going to connect the push button to ground on the breadboard. Now, this is what we have here. Our push button is connected on one side to pin 23 on the ESP32 and on the other side to the ground. The behavior we're expecting here is to get a low signal from ground whenever the button is pressed. So let's head to our code and check it out. The first thing we're going to do here is configure pin 23 as the button pin. We'll then create a variable to read and store the push button state. On the setup function, we're going to use pin mode to initialize the button pin as an input. That means we can read the state of that pin. And we're going to do that on the loop by calling the digital read function, passing the button pin as an argument. So when the button is pressed, it will connect the ESP32 pin to ground, which means its state will be low. So the behavior we're expecting here is that when the button state is low, we have the button down, but if the button state is not low, then we have the button up. Now we just need to compile it, upload to our ESP32, and open up the serial monitor to see if we're getting the expected behavior here. All right, I'm not pressing the button, but we are all over the place, getting both high and low signals. Definitely not what we expected. But when I do press the button, we start getting only the button down. So we're only getting the low signal whenever the button is pressed. So at least this part of our code and our circuit is working. So what's happening here? By running our code, we just saw that we're not getting a consistent behavior when the button is not pressed. So this is a simplified version of our code. We're initializing pin 23 as an input and reading its state using the digital read function. This function will return either high or low depending on the pin state. But what is happening with pin 23 when we are not pressing the button? Sometimes we're getting high and sometimes we're getting low. So our serial monitor was printing button down, button up, even though I was not touching the button. When this behavior happens, getting randomly high and low signals, we say that the pin is floating. Let's understand what that is. So when we are pressing the button, we are connecting pin 23 to ground. In this case, we expect the pin state to be low. And this is happening as expected. Once I press the button, we would get the button down message. But when we are not pressing the push button, pin 23 is not actually connected to anything. When nothing is connected to our pin, it can behave erratically. It will pick up electrical noise from the breadboard, from other components, from the wire, from the electronics that I have around me. So digital read ends up returning high and low randomly. When this happens, we say that the pin is floating. So how can we fix this? What we want is for pin 23 to have a known state whenever no one is pressing the button. We need that in order to be able to correctly detect when the button is being pressed. One common way to achieve this is by using a PullUp Resistor. A PullUp Resistor will connect our pin to power, which means that its state will be high by default. Since our button is then connected to ground, when the button is pressed, pin 23 will then change its state from high to low. So let's see how the PullUp Resistor works. Pin 23 is connected to the push button, but it's also connected to power through a PullUp resistor of 10K ohm. This is called a PullUp resistor because it guarantees that pin 23 will get a high voltage all the way from here whenever the push button is open or not being pressed. The push button, the other side of it, is also connected to ground. So when we press the button, the switch over here closes, and pin 23 will start getting a low signal. This happens because electrical currents will travel through the path of least resistance. The PullUp resistor between the power and pin 23 will actually add resistance to that path whenever we have the button pressed. So this way, we get our consistent behavior. High when the button is not pressed, but low when it is pressed. So let's change our breadboard to get our PullUp resistor. So one way to do this would be to slightly move the green wire connecting pin 23 to the push button to allow us to add a 10 ohm resistor between the push button, or pin 23, and the power supply. This is fine, and it works as expected, but I don't recall seeing any resistors on our list of required hardware. So how are we going to solve this? The cool thing about the ESP32 and also Arduino boards is that they have internal PullUp resistors that we can use by just changing one small thing on our code. So this is the code that we have right now, using pin mode to configure the button pin as an input. We need to change something on our code to enable the internal PullUp resistor connected to pin 23. This is done by using the constant input PullUp when setting the pin mode. By using input PullUp instead of just input, when configuring our pin, we're enabling the internal PullUp resistor that we have on the ESP32 board, and we're no longer going to need the external resistor. So we can just remove this and keep our circuit as it was. So let's make this change on our code and see what happens. The only thing we're changing here is enabling the internal PullUp resistor by using input PullUp when configuring the pin mode of button pin. This will guarantee that the button pin on the ESP32 will be getting a high voltage whenever the push button is not pressed. So let's compile this code, upload it to our board, and see if we're getting the expected behavior. Can open up the serial monitor, and there we have it. Not pressing the button and getting a button up message on my serial monitor, but then once I do press the button, I'm getting a button down. So now we have a consistent behavior for our button that we managed to get using an internal PullUp resistor. Now that we know how to work with push buttons, we can create our call waiter button, merging the knowledge that we just got with the knowledge from Module 1, connecting to AWS IoT Core and sending MQTT messages. But before we start working with the call waiter button, there's something else we need to cover. We learned that the ESP32 loop function runs over and over. It might be that we just want to do one thing inside a function, like read the button state, but we might want to do more things. On the next module, we're gonna learn how to read sensor data. We'll then send that sensor data to AWS IoT. We'll also want to keep having our push button and having it behave as a call waiter button. Another thing we might want to do is receive data from AWS IoT, like we did on Module 1, and then turn on or off the lights based on whatever message we received. So we have all this code inside our loop function. But then what happens if the loop is currently executing the code that reads the sensor data and someone presses the button at exactly that time? Our loop will keep executing instruction after instruction. But what if when we finally reach the code that checks if the button is pressed or not, the button has already been released? In that case, we would completely miss the push of the button and never call the waiter. So how can we avoid this and at the same time make sure that whenever the button is pressed, it will have priority over the other instructions? One way would be to have a program that does nothing else besides checking if a button is pushed or not. But we want to write programs that do more than that, while at the same time being able to correctly read the push of a button. So we basically want our program to stop what it's currently doing and register the push of the button whenever that happens. One way to do that is by using interrupts. They allow us to make sure that our program will always respond to specific input. They are great for solving timing problems like the ones that can happen with the push button, while at the same time, they free the microcontroller to do other things while the button is not being pressed. So how do interrupts work on Arduino? We have a function called touchInterrupt that takes 3 arguments. The first one is the GPYO pin in which we want to enable the interruption. The second one is what we call an interrupt service routine, or ISR. This is the function that will be triggered when the interruption happens. Finally, the third argument is the mode. This defines when the interruption should be triggered. So let's write this on our code. The first argument is the pin on the ESP32 where we are going to configure the interrupt. On our case, this is the button pin, or pin 23, that we defined over there. The second argument is the interrupt service routine, or ISR. This is the function that we are going to call whenever the interruption happens. But there are a few things we need to keep in mind when creating an ISR. The ISR does not take any arguments, and it also doesn't return anything, so its return type should be void. It should be as short and fast as possible, since it will stop the rest of our program from running. And we also cannot call the delay function that we used on the last module that stops our code for a specific amount of milliseconds. That delay function cannot be called inside of interrupt. And we typically use global variables to pass data between an ISR and the rest of the program. To make sure that these variables are updated correctly, we should declare them as volatile. This will tell the compiler that such variables might change at any time, so the compiler will always reload them whenever they are being referenced. So we're going to call our ISR button pressed. So we can start writing this function, and we're going to use a flag variable that will tell us if we should call the waiter or not. This will be a volatile variable because it will be used inside the interrupt function, and it will be initialized to false. So inside the ISR function, we're just going to change the call waiter flag to true. Like we mentioned before, we want this to run as fast as possible. So the loop will be the one responsible for actually publishing a message to AWS IoT. The interrupt function will only change the flag. So inside our loop, we're going to check if call waiter is true and then do something based on that, like sending a message to AWS IoT and setting the call waiter flag back to false. So now the only thing missing to specify on our interrupt is the interrupt mode. The interrupt mode defines when it should be triggered, and there are 5 constants that we can use as the interrupt mode. First one is low, which triggers the interrupt when the pin is low. Then we have high, which triggers the interrupt when the pin is high. Change will trigger the interrupt whenever there's a change from high to low or low to high. Rising will trigger the interrupt when the pin goes from low to high. And falling will trigger the interrupt when the pin goes from high to low. If you remember our circuit with the internal PullUp Resistor, this is exactly what we want. The ESP32 pin is receiving a high signal when the button is not pressed, and it receives a low signal when the button is pressed. So our interrupt mode will be falling. So let's configure this over here and take a last look at our circuit so we can move on to the code. Over here, we have pin 23 connected to the push button and also to the internal PullUp resistor that we configured on our code. The button is connected to ground. So whenever we push the button, it goes from high, that it's getting from the internal PullUp resistor, to low, that it's getting from ground. This is what the breadboard with the circuit looks in real life. I can show you mine right here. And now let's take a look at our code running. Here is our code, and we're going to use the Arduino JSON library to send MQTT messages with the JSON format. To install it, we'll open up the library manager and search for Arduino JSON. We're going to install the first option that we have right here. You can see that we're still using the secrets file and calling our thing ESP32 like we did on a previous module. But now we're publishing the data of the call waiter button to this topic called callWaiter/button. So we need to update our policy to allow us to publish messages to this topic. On the IoT console, we're going to go over to Secure, Policies, the Let's Build policy, and we need to add permission to publish messages to the call waiter topic. We're going to edit our policy, add callWaiter/button. We can save this and now go back to Arduino. Over here, we're defining the table name and also configuring the button pin. We're using the same libraries to connect to Wi-Fi and AWS like we did before. And we have a flag that tells us when was the last time the call waiter happened, and then the call waiter flag that tells us if we need to call it or not. On the setup, we are configuring the button pin using the internal PullUp Resistor. And we are also attaching our interrupt function. Whenever the pin from the button is falling, going from high to low. This is our interrupt function. It will record the current time, and we don't want to call the waiter several times inside the same second. So we're just making sure that the last time we called was more than 1 second ago. We're going to change the call waiter flag to true, and then update the time that we last called the waiter. On the loop function, we're calling our MQTT client loop method. And then if the call waiter flag is true, we're going to create a JSON document with the table name, device name, and device time, serialize it, and then publish it to the call waiter/button topic. We're going to reset the call waiter flag back to false. So let's compile our code and upload it to the board. We can also open up the serial monitor and here we can see that we are now connected to AWS IoT Core. Going to the console, we're going to open the MQTT test client and subscribe to the call waiter/button topic. Now, whenever we press the button on our circuit, we should be getting a message here. You can see that we just got a message with all the data on the JSON that we assembled. Another one, but then if I press the button several times at once, we're only getting one message because we're making sure that we're not sending multiple messages in less than 1 second. On the serial monitor of the Arduino IDE, we can see that we perform the call waiter function, sending the messages to AWS IoT 4 different times. This is it. We have our call waiter button detecting when it is pressed and sending messages to AWS IoT with the device and table information. I hope you had fun learning how to work with push buttons and helping Richard and Mary create their own IoT call waiter button. Join us on the next module to learn how to work with sensors, relays, and how to connect our IoT messages to other AWS services like DynamoDB and Lambda. Thank you.
Well, hello there, you amazing tech people, you. Listen, thank you so much for stopping by to check out this video. However, there is so much more great content out there to be found, so make sure to subscribe to the Build on AWS YouTube channel, and while you're at it, click that bell icon to be notified about the latest and greatest in videos made by builders for